Drink it. It's quick, yep.
I just realized that I'm not sure how many of us would have seen or be like really familiar with the total differentiation idea you're doing where you like take d of something without taking also a d on the bottom.
It doesn't matter. It's I've set everything up so it's completely element. I'm not assuming really anything other than partial derivatives. Okay, so let's see where we're at. So I have functions. If I take the exterior derivative of that, I get a one form. If I take a one form, let's say omega, I take the exterior derivative, I get a 2 form. Guess what I get if I take the exterior derivative of a 2 form?
3 form.
Good. So eta in here. The eta will be a 3 form. Okay. From this perspective, you believe that are you convinced that it's natural to refer to functions as 0 forms? Because the exterior derivative bumps up the degree, or the type. So if I say a form of type k, I mean a k form, or degree k, I mean a k form. We can see that it's bumping up the degree by 1 every time, so it's natural to refer to these as 0 forms. And we'll write it like this. Okay, so for those who missed the lecture just then, we have this operation. So here dx, dy, dz, these are 1 forms, of course. And we have this operation dx wedge dy, which assigns the area of the parallelogram. So if I took 2 vectors u and v, u wedge v is the area of this parallelogram. What are the 2 key properties of the wedge product?
The anti-symmetries.
Anti-symmetry, so u wedge v is minus v wedge u.
Nilpotence.
Nilpotence, u wedge u is 0. Just because the words can be scary, that's why I chose it. That's nilpotence, this is anti-symmetry. Okay, for those of you who are over-enthusiastic, here's an exercise to do. It's like a party problem. Take it to your friends. Show that anti-symmetry implies nilpotence.
Alright, so
It's an exercise.
you
We're not doing it now. It's just for everyone to sit with and just have fun. It's just you want to struggle, and if you struggle, good. If you don't, even better. If you get sick of it and just want to see how it's done, then you can watch my video on what is area. Okay. I go through the whole wedge product nonsense in there. Okay, so what do I want to say now? I want to understand, if I look at, if I apply the operator twice, this is what I started with in the lecture. I want to understand the effect of that. So what I will do is write it up here. So let f be a smooth function. It's a what form? A 0 form. let f be a smooth function, then df, let's just take 2 dimensions for enjoyment. Fx dx, fy dy. Yep. I want to compute the exterior derivative of this. So I want to compute d of df. How do I compute the exterior derivative of a one form? Just take the component functions and take the exterior derivative. So I take the exterior derivative of fx, so I get fxx dx, fxy dy. And now I have to wedge with dx. I have yx dx plus fyy dy, and I wedge with dy. Expand it out as per usual. Fxx dx wedge dx plus fxy dy wedge dx, fyx dx wedge dy, fyy dy wedge dy. It's kind of the same thing over and over again, right? What do we do now?
Cancel the other stuff.
Nilpotence tells you the following terms vanish.
Now fyx minus fxy dx.
And now I can use anti-symmetry to flip this around, giving me fyx minus fxy dx wedge dy. But Clairaut's theorem tells us that this has to be 0. By Clairaut's theorem. What do we see?
The directional, the right triangle direction of the exterior derivative of the exterior derivative, the truth one is always 0.
So remember that if I can write a one form as df, then at least when we looked at vector fields, I said that was a gradient field. Right? So if I look at vector fields of this type, these were gradient fields. Now the one form associated to a gradient field is then df. And I didn't require you to remember this language, but the word for this is exact form. That's an exact one form. And what we're seeing is that the exterior derivative of an exact one form is 0. Okay. Do you remember that yesterday I showed you that if f was a gradient field and was pi plus qj, what were the conditions on the partial derivatives? Try again? Does anyone remember fully? It's the opposite of what you would think. You know, you would think px and qy, don't think that. It's the opposite of that. It's qx is qy. Remember that? That was a necessary condition. So if gradient field, then this has to be true. But it's not necessarily true that if this is true, then you're a gradient field. What's the point? It's an exercise for everyone to see that this calculation here implies that. Remember I said your ears should perk up for fundamental theorem of calculus, Clairaut's theorem. I gave you a vector field yesterday that you should really pay attention to. This equation here, d square is 0. By d square I mean the exterior derivative applied twice. That's another one. Okay? This is the fundamental theorem of calculus that I'm teaching you, but this is the other thing I'm teaching you. Okay? If you understood the meaning of this, you'd probably be the smartest person alive today. We don't understand what this means. In fact, just one moment. If we look at the start of my notes, the opening quote is, "If only I could understand the meaning of d squared equals 0." And that's a quote by Henri Cartan, who was one of the greatest mathematicians of the 20th century. This equation has led to what's called cohomology, and what we're learning in vector calculus is a kindergarten version of cohomology. Cohomology is a tremendous development in mathematics. Yep.
What if f is in R cubed instead of R squared?
Then you repeat this entire thing, and you get the same. That's an exercise. Do this in R3. If you want to get confused about cohomology, by the way, you can look at Chapter 5. Chapter 5, the high road to vector calculus. I'm not assessing that because that would be abuse. It essentially says, if you knew cohomology, I can essentially give all the theorems of vector calculus in like 20 minutes. So that's what that's for. That's why we're only doing chapters 1 to 4. Okay. So we've seen that, let me talk about, so we've seen wedge products, we've now seen exterior derivatives of the one forms associated to gradient fields. Let me look at an example of how this may be of some utility. Let f be, let's say, 2x plus y plus y minus z jx plus yz x. What is this? One form, two form, three form, what? It's a vector field. Vector fields can be associated to what type of form? One forms. Not two forms, only one form. Okay, so I want to check if, what do I want? I want to check if f is a gradient field. Or at least try. I'm hoping it goes the way I want. If it doesn't, then that's unfortunate. So what I'm going to do is I'm going to look at the associated vector field omega f. So I take 2x plus y dx, y minus z dy, y z dz. Now, if f is a gradient field, then omega f should be the exterior derivative of a function, right? So let me just spell this out. So if f is now an f, that implies that omega f is df, and by this calculation I have just done, this implies that d omega f would have to be 0. So in particular, if d omega f is non-zero, then this is not true, and therefore this is not true. Yeah? So it gives us a way of testing whether a vector field is a gradient field or whether a one form is exact. Okay, so let's compute it. Okay, so let's compute d omega f. What do I get? Well, if I differentiate 2x plus y in the x, I get 2dx. And I should get dy. There's no z terms, that's fine. X. Next term, I should get a dy minus dz. Wedge dy plus z dy plus y dz wedge dz. Okay, let's expand it out. 2dx wedge dx plus dy wedge dx plus dy wedge dy minus dz wedge dy plus z dy wedge dz plus y dz wedge dz. Yeah. Now what? Nilpotence. Kill this, kill that, kill that. What remains? I'll write this as minus minus dx wedge dy. I'll write this as dy wedge dz. And I'll write this as the same. Z dy wedge dz. Is that 0? It's not. What does that say? What? It's not a gradient field. Okay. That's not too bad, right? This is kind of fun. Yeah. I want everyone to practice this though. Don't think, oh, it's completely elementary. You should be lightning fast at it. You should be able to compute the exterior derivative of a 20 form in 10 minutes. Not 10 minutes, that's way too long. Preferably 30 seconds. You should be able to do it as quicker than me. I mean, I'm older than you, so you guys are faster than me. And so it should be fine. Okay. I also have here just a remark that the exterior derivative of, sorry, not the exterior derivative. If you wedge a K form and an L form, for instance, a 1 form and a 2 form, then you should get a 3 form, right? The degrees, the wedge product is additive on degrees. Let me show you now a further fact. Actually, no, I'm going to leave it as an exercise. Show that, and by show that, if you don't want to show it for an arbitrary thing, you can do it for a specific one. That's fine. Show that let's say a 2 form, no, I want a 3 form on R2 is always 0. And similarly, if you were to take a 4 form on R3, that's always 0 as well. Okay, so if you wedge beyond the dimension, the thing is entirely killed. Okay? Yep.
Just a question. Does the d squared equal 0 and the gradient field is infinite?
Is it an infinitely? The d squared is 0 is always true. we use that to show that if f is a gradient field. Oh, hang on, sorry. Restate your question.
Is it d squared equals 0 if and only if f is 3?
Well, the meaning of d squared is 0 is exactly that if I take d of a gradient field, or more precisely the one form associated to a gradient field, this is always 0.
Oh, sorry. Is d omega equals 0 if and only if?
If and only if, it will depend, it's true. The if is true, the only if is more subtle. We're going to get to that. So far I've only made if statements. Yeah. That leads to, it's exactly this thing called homology. So when we talk about simply connected domains, that's where this kind of if and only if stuff comes in. Does anyone else have any questions so far? Yep.
With the notation in the notes there, you've got like lambda to the k, wedge lambda to the L equals lambda to the k plus L.
Yeah.
Is that actual notation you use to wedge two spaces, or is that just to indicate that two like objects, two forms from?
Yeah, this is it's a meaningless notation really, because lambda k denotes a space of things, and lambda L denotes a space of things. So what I mean by here is, if you take lambda, what I really mean is this. The wedge product is a map which takes in a k form and an L form outputs a k form. That's really what I mean. So, okay, compute the exterior derivative of a one form, good. I have this nice little picture here. I have these little warning signs, which are nice. Okay, here's the proof we just did. And here is the key picture so far. So we have seen that functions are the same thing as zero forms. Vector fields aren't the same as one forms, but you can pass between them interchangeably. And if you want to go between forms, that's carried out through the exterior derivative. Okay? When we do that Barry's world thing that I made up, this is going to be one of the key rules. Okay, so I have still 20 minutes to torture you. So what I plan to do is each week I want to get started on the week ahead so that you can have something fun to do over the weekend. And so we're going to start looking at the differentiation theory. So recall in the opening propaganda speech that the way the course is run is through functions, derivatives, integrals, FDC. We're now done with functions. The functions that we have in this course are vector fields and one forms, or more generally, two forms and three forms and so on. That just reminds me I haven't defined what a three form is. A three form is this. Let's say A f is a function, and then I have dx, wedge, dy, dz. Okay, it's like a volume, something you would integrate over three-dimensional. And now what we're going to do is we're going to look at the differentiation theory of the subject. And what is beautiful about doing things in terms of forms is that you can actually see that it's a differentiation theory. If I was to not use forms, then I would give you these two formulas here for curl and divergence. You would pretend you understood them. You would have no idea that they were derivatives of vector fields, and if you did, that would just be a bluff. But I'm going to show you that is indeed the case, and so let's take a look. So I told everyone that they needed to get very, very good at cross products. That's indeed the case, but we won't have to get too good at them because we're just going to take exterior derivatives. Nevertheless, if I have a vector field, F is, let's say, P, I, Q in the J, plus R in the K, these are functions, P, Q, and R, then what I want to do is I want to look at something which I call the curl of F. And this is a measure of the rotational aspects of this vector field. Okay? And we're going to understand rotation as a derivative by the end of chapter 2. So, okay, what is the curl of a vector field? You take this grad. Here I'm viewing grad not as an operator, but as a vector. This is the kind of classical vector calculus approach. It's the vector which is exactly given by that. Okay, so it's the partial derivative of with respect to x in the ith direction, y partial derivative in the jth, z partial derivative in the kth. I then take the cross product with my vector field, which by definition is the determinant of the following matrix. Partial x, partial y, partial z, p, q, r. Who does not want me to explain the cross product? Who wants me to explain the cross product? I see in the middle. Okay. At least computationally, the cross product is given by the determinant of this matrix, and the determinant of this matrix is given by hiding these entries and computing the determinants of the minors. So let's get a handle on the computation first. So we take I hat, and now I need to compute the determinant of partial y, partial z, q, r. Then I end up with this j, but it's minus. There's kind of this checkerboard thing where it's plus, minus, plus. And I compute I hide that, and I get partial x, partial z, p, r, and then k hat will be x, y, x, partial y, p, and q. Okay? This is what we would have learned last semester. And then just for completeness, this is ry minus qz minus j, rx minus pz is k, qx minus py. What does that look like? Very close to that condition of a gradient field. What do we require? If we have a gradient field, what does this term equal? 0. It equals 0. That is not random. Okay, so
Wait, so if we've got a gradient field, the curl is 0 in the k direction?
if f is a gradient field, this is on R2, remember?
Oh.
So if I take, let me spell this out because it's worth spelling out. If f is a gradient field on R2, then let's say p pi plus qj, R is 0. If R is 0, what I have is that the curl is the determinant of this matrix, partial x, partial y, partial z, p, q, 0. That is 0 because there's no R. This is 0 because there's no z. This is 0 because there's no R. And this is 0 because there's no z. Right? It's only x and y that's a vector field in R2. So what I end up getting is qx minus py in the kth direction,
Which is 0.
which is 0
It's a gradient field.
if it's a gradient field.
So gradient field for the curl is 0.
0 if f is something's going on.
In R3 also that's 0, right? Ry minus q z. Because Ry would be just fz and q would be. Sorry,
If
not
it's a
Ry.
gradient field, the curl will be 0 in general. Yes, that's
Yes.
exactly right. That's exactly right. But I haven't done the laborious calculation you do, which is exactly, you would exactly get this term out. So what are we observing here? Well, we're seeing, okay, we're seeing that nabla cross nabla, what do I want to say here? Yeah, nabla f. This is what we just showed, at least on R2. It's an exercise to do it on R3. Everything I don't want to do, that's an exercise. So, what's going on here? Well, we also saw that d of df was 0. You can already kind of see how curl is going to become a derivative, right? You can see the analogy here. Because nabla f is the vector field associated to this one form. On one forms we have the exterior derivative, but now I can also take the cross product of this vector field. They're behaving very similarly. I'll show you the formula for how to get from one to the other, but the analogy is already quite clear. Okay, so let me give a definition. Something to take notes on. If f is a vector field with curl f equal to 0, what 0 is this? It's the 0 vector, that's right. Because the curl outputs a vector, so it's the vector field. This is also a vector. This, it depends. You think about it as the 0 in two forms. If you understand what the 0. Yeah.
So is it a vector or is there a vector field?
A vector is a vector field. And so the 0 vector is a 0 vector field. So 0 at every point. So if f is a vector field with this property, then we say f is said to be irrotational. That's the definition of an irrotational vector field. Let me give some pictures. So, this first one gives an example where the curl is positive. Now, who can see why that is absolutely meaningless, that last sentence? The curl is positive.
Because it's a direction.
Vectors don't have direction.
Okay, I mean the curl direction.
The curl direction. But curl is a vector. How do I write that the vector is positive? What does it mean for that to be positive? Clockwise, anti-clockwise, but how's that from actually? You can't work with the definition and then change it to fit what you like. This is a vector. Say again? The k component. Why can we speak of only the k component? Exactly. So I have a vector field on R2. If I have a vector field on R2, then we computed the curl already. We get only a kth component. And therefore, yeah?
Because
Exactly. So it's a cross product. A cross product outputs for any two vectors a third one which is orthogonal to both. Let's do something like this. So I take a vector, another one, and it outputs one that's mutually orthogonal to both of them. So if my vector field sits in R2, the curl sits exclusively in R3, in the third component. And if I took the dot product with k hat, I would get a scalar, and scalars can be made positive or negative. That make sense? So it's fundamentally because of the vector field being two-dimensional, or at least sitting in R2. So anti-clockwise is positive curl, clockwise is negative curl, and here are some examples illustrating exactly that property.
I'd like to see one with zero curl.
You want to see one with zero curl? Here's this is one with, this would be zero curl. Shoots out. There's no rotation. Okay? This is going to be the divergence, which we're going to look at very soon. Okay, so let's have a look at just doing a calculation of the curl. So you have plenty of stuff to do when you what's it? 10:50. Okay, let's do a quick one. Let's say f is x, z, y, so xi plus zj plus yk. Curl of f is determinant I, j, k, partial x, partial y, partial z, x, z, y. Take the determinant, we'll get partial y, partial z, z, y, j hat, so we hide this, hide that, I get partial x, partial z, x, y, plus k hat, hide that, I get partial x, partial y, x, z. I want cross products to be computed this quickly. Yep.
Why is the y and the z swapped in the table?
F is z.
Okay.
What? Yeah, definition of the vector field. Okay, so I now compute these. What do I got? I got the y partial derivative of that, that's 1, minus 1, minus j, that's 0, 0, plus k, that's 0, that's 0. Is this vector field irrotational? Good. Okay. What did we do? What did we do today?
We learned about curl.
We learned about curl. What else did we learn about?
We learned about two forms.
We learned about two forms. What else did we learn about? The wedge product. We were tortured to death with the wedge product. We're now getting closer to the establishment. We're now going to be initiated into the Durand theory of vector calculus. We can become vector calculus snobs that we all want to become. What else did we learn? D squared equals 0, one of the most important equations in modern mathematics. What else did we learn? Antisymmetry, and what's the other one? Nilpotence. Why is nilpotence true? What's the geometric intuition? Area of the line. What is the wedge product of two vectors kind of representing? 2, 1, 4. Area of the parallelogram. It's a little more subtle than that. It's not just area, it's Signed area, because it's allowed to be negative. What is the exterior derivative of a one form? What? It's a two form. Vector fields are associated to two forms. True or false? False. False. Good. Functions are 7 forms. False. Functions are 0 forms. True. What else did I cover? Surely I covered more than that.
External derivative of the
Yes, so if I take the exterior derivative of the one form associated to a gradient field, it's always 0. Why was that true? What was the key point? So C ends with Leroy's theorem. Good. What else? Let me hide this. Anti-clockwise rotation. Positive or negative curl? Why is that meaningless in dimension 3? There's no direction for an arbitrary vector, but if the vector field sits in R2, the vector field, the curl points up in one direction, so I can associate a number to it. Okay? Does the exterior derivative increase the degree or decrease the degree?
Increase.
It increases it by how much?
1.
1. Good. Okay, you can go home. Also, what are we doing when we go home and open up our computers? Subscribing to my channel. Good.